talk a little more about catalysis. So, on some of the different things that might be involved in catalysis. So, proximity. So, the first thing that an enzyme might do in the realm of catalysis is it might just bring the groups that need to interact close together. It just brings the groups that need to interact or react, if you will, close together. And so that's one way. So it can be involved in catalysis. Kind of ends up being kind of an entropy consideration in this case. So note that it also can involve changing the orientation so that the right side, the correct, I say right, let's not go right and left, but the correct side of the molecules that interact are the ones that is the part of the molecules that are actually bumping into each other, if you will. So it can also affect the orientation, this proximity effect. You can also look at strain effects. So in this case, in a chemical reaction, what happens? Net result? Bonds are broken and bonds are formed. Old bonds broken, new bonds formed. What does it take to break bonds? Energy. And that's usually what we like to think of as our activation energy to the top of the hill. And then what happens when you make new bonds? It releases energy, and that's the other side of the hill. So notice to get the chemical reaction to go, though, you got to break those bonds and form that transition state. Sweet. So sometimes the bonds in the substrate can be strained, stretched, twisted, bent, in some way strained, which kind of helps you get up towards the activation energy, if you will. So, or at least makes breaking that bond that much easier, so lowering the activation energy that way. Talk about electrostatic effects, and these can come up in a couple of different areas. So let's say your substrate for a particular enzyme has a negative charge. What might be a good amino acid to have in the active site to help bind that substrate? What's that? A positive one. What are the two big positive ones? Remember they're positive at pH 7? Lysine and arginine. It'd be perfect to have a lysine or arginine in the active site because they're positively charged at pH 7. It'd be perfect. So things of that sort. Talk about acid-base effects. So question for you. Rely on your OChem knowledge here. Which one of these is a better nucleophile? Bottom one definitely is. Better nucleophile, right there. But what if this is actually what's present on your substrate? And it's going to be the nucleophile, but you'd so love it to look like this. Well, it'd be so convenient if you had an amino acid that was a base. And it just came and said, you know what, I'm going to take that H off you right here. That way you can look like this, and you'll be much more reactive. And so we can talk about acid-base effects. Sometimes those can increase the nucleophilicity of a certain substrate or increase the electrophilicity as well, vice versa. Both can happen. And so acid-base catalysis can also play a role. This is really, really common, by the way. And then finally, covalent catalysis. So what's covalent catalysis then? Say one more time.
Making covalent bonds that can be broken.
Good. You're actually making covalent bonds to the substrate temporarily because they are going to be broken eventually. So here's the deal. When a substrate binds to the active side of an enzyme, a lot of the time, a lot of the stuff we've been talking about up till now has dealt with just anything that's not covalent. Electrostatic interactions, hydrogen bonding, things of this sort for the interaction between the enzyme and the substrate. But in covalent catalysis, the enzyme actually covalently bonds to your substrate temporarily, just to help the reaction along. So in this case, temporarily bonds, and then when things are done, that bond's going to get broken. That way the substrate, which has now been converted into the product, gets released. So it's a temporary covalent binding. So and that's pretty common here and there as well. Cool. But all these can be ways that enzymes affect catalysis.